or it could be the magnetic personality of our speakers, right? Everybody to come in. Okay, I believe there's probably the number of people that are in the building. So you might as well start right now. I think it's a minute or two early. It's a great pleasure hosting Dr. Lee Norris, representative at Schlumberger. And his history goes is he's an undergraduate mechanical engineering from UT Austin. We have another UT undergrad from here. And he did his PhD in mechanical engineering from Stanford under the tutelage of Professor W.C. Reynolds, one of the biggest names in the turbulence area. Then he joined Exxon Upstream Production.
Well, it's called Exxon Production Research in those days.
Exxon Production Research. And spent 20 years over there before moving to the SPT Group. Most of you who have been using SPT product, OLGA, are pretty familiar with what SPT does. And then SPT last a year and a half ago got bought by Schlumberger, and by default, even though he didn't apply for a job for Schlumberger, he became a Schlumberger employee. So let's welcome Dr. Lee Norris for an exciting talk about the multi-phase flows. And this seminar is being graciously sponsored by Schlumberger, or Dr. Norris, Eddie for hosting him, and our College of Engineering startup money for the ethics seminars. So, thank you.
Well, I appreciate you guys coming out. I'm really gratified and astounded that so many people here. The weather's wretched. You don't have to be here. There's not even any cookies, are there?
My apologies. That was also canceled.
It's always sort of the standard thing. No cookies, no students. But you guys are, gee, I'm blown away. What I'd like to talk to you about for the next 45 minutes or so is multi-phase flow and some of its applications in production operations. And I'd like to do that in sort of 4 different topics. First of all, I'd like to talk a little bit about some multi-phase flow works. I don't know how to put it more elegantly than that works. Now, some of you working in the field may be very aware of this. Some of you may not. So bear with me if I'm telling you some stuff that you already know. I'd then like to talk in general about some of the applications of transient multi-phase flow. Why is it important, particularly in the particularly in the upstream, although not limited to the upstream production, oil production. But why it's so important there is an example of some of the things that transient multi-phase flow is good for. And then, since this is a computing seminar, I'd like to go in at least briefly to the structure of OLGA. And I think that you'll find that OLGA is a good deal simpler than, say, Fluent or some of the CFD programs. But the trade-off with that is, of course, it runs a lot faster, and you can use it for more engineering applications. And then finally, I'd like to talk a little bit about a specific project that I've been involved in, and I think it's really quite important, and that's horizontal fractured wells, shale wells. Many of you may be aware that that's one of the most active portions of the oil industry these days. And I think you'll see that the transient simulations in OLGA can shed some light on the sometimes very puzzling dynamics of shale wells. So that's where we're going in the next few minutes. First of all, let's look at multi-phase flow works. And what do we mean by multi-phase flow? In general, at least what I'm talking about, is multi-phase flow of several admissible phases simultaneously present. Now, I also need to make the caveat that I'm going to be talking about multi-phase flow in pipes. So I know that a lot of you are interested in reservoir and flow through porous media, and not only will you see that that's mostly not what I'm talking about, you'll see when I'm forced to talk about it, how absolutely pathetic we are at it. So suggestions are solicited. But we're talking about flow of, could be a bunch of stuff, gas and droplets, liquid hydrocarbons, free water, and some other minor phases. But mostly what I will be talking about is the flow of immiscible fluids, in particular vapor and liquid. I may talk a little bit about the flow of the three-phase, vapor, hydrocarbon, liquid, and water. But to a certain extent, the water hydrocarbon liquid flow is sort of derivative from the methods of vapor liquid flow. So mostly I'm going to be talking about vapor liquid flow. That's certainly the most industrially important, and the ones that OLGA does best. The first quirk is that the fluid may choose to distribute itself across the cross-sectional area of the pipe in a number of different ways, or different flow regimes that depend on a bunch of things, but most notably on the angle of inclination of the pipe and the relative flow rates and the absolute flow rates of the vapor and liquid that we're talking about. For example, sort of the two main categories of segregated flow and, well, segregated, intermittent, and distributed flow. And the segregated and distributed flow are the easiest to see. If you have a vapor and a liquid flowing in a horizontal pipe, and the vapor flow rate is low, liquid flow rate is low, what happens? The liquid settles to the bottom, the vapor to the top, very much just like the flow of the Mississippi River running by the campus. That's pretty simple, probably the easiest to analyze. But as the for relatively low liquid flow rates, as the vapor flow rate over the top of that increases, you get the generation of interfacial waves, very much akin to the growth of ocean waves by the wind blowing over it. In fact, one of the first relevant papers on this was done by Jeffries in 1923, examining through Bernoulli effects the growth of waves over the top of a liquid. So the first thing that happens is that you can generate growth of waves. Now, as the gas flow rate increases more and more, some more physics come into account. Two new effects come into account. One of them is liquid droplet entrainment, and that is on the tops of all these waves, liquid droplets can actually get stripped off, and they can be suspended in the gas flow. But that's not all that's happened. There's something even funkier happening, and that is due to since this is a non-circular cross-sectional area with the stratified flow, you generate secondary flows in the gas section on the top. These secondary flows will actually sweep with the interfacial shear stress, the liquid layer up around the walls of the pipe, till eventually the two films meet at the top, so that not only do you have droplets in the middle of this flow, you actually have an annulus of liquid around that's maintained by the secondary stresses. Now, as you might guess, this isn't entirely symmetrical, as I've indicated here. The film layer tends to be thinner at the top than the bottom. But what is frequently called an annular flow, a mist flow, is really an annular mist flow, where you get this liquid flowing in an annulus on the pipe wall, and a core of droplets in the center. Okay, that's for the case with making a lot of gas and a lesser amount of liquid. Let's go at it from the other side. If you have a little bit of gas in a primarily liquid flow, it's pretty simple. You get a bunch of bubbles that travel along the top of the tube. That's bubbly flow. Or the other way around, and again, so the one I just talked about is that if you really have high velocities in the core of the annulus goes to almost nothingness. It's primarily mist flow. So you say, well, you already have, what is it, 1, 2, 3, 4, 5 different flow regimes. But it gets more interesting. The really interesting group, and we'll talk about a little bit more detail, are the intermittent flows. And you can start to kind of see how they are intermittent between the two classes that I've talked about comparable to the diameter of the pipe. It breaks down into a slug flow. Or alternatively, another heuristic for the same phenomenon is that as these waves become bigger and bigger until they bridge, you get broken down into slug flow. And slug flow is one of the most industrially interesting and vexing of the flow regimes because in addition to the normal concerns of pressure drop and average liquid flow rate, you get these big fluctuations in instantaneous liquid flow rate, which can cause great vexation to processing facilities downstream. So I perhaps have spoken at some length in horizontal flow of the fact that the liquid and vapor may choose, for sometimes arbitrarily seeming reasons, distribute themselves across the pipe cross-section area differently. Same thing happens in vertical flow, except the only difference here, there's no preferred direction. I mean, the liquid is not, the liquid tends to settle at the bottom of the pipe, but it's not going to settle to the northeast side of the pipe. There's no preferred cross-pipe direction here. But the results are still similar. You still have separated and distributed flows. You still have slug flow. You still have dispersed bubble flow. You still have angular flow. The only thing that's different is that you no longer have stratified flow because there's no reason for it to stratify one side. Now, one question you're probably already asking is, well, what happens in inclined pipe? And the transition between horizontal flow and vertical flow is not really real smooth. It turns out that when you have an inclined pipe, it doesn't make much inclination, like a degree, a half a degree, cause for profound change in these flow regimes. Vertical flow is a little bit more forgiving. But that's still a research topic, is flow regime changes in inclined pipes as a function of angle of inclination, as a function of different phase flow rates. So that's point one. Point number one, the flow may choose to distribute itself in different ways across the pipe cross-sectional area. You just got to learn to live with it. Another thing, too, that I think is handled really rather better now is that you become obsessed with hydrocarbon or fluid phase behavior for obvious reasons. If you don't know the relative amounts of liquid and vapor in your flow, you're really sort of helpless to do anything quantitative. And of course, in hydrocarbon mixtures, particularly multi-component hydrocarbon mixtures, i.e. all oils and gases, you have various phase behaviors. And in fact, basically the difference between an oil and a gas is that in a gas you have more lighter fractions, in an oil you have more heavier fractions. They have different phase envelopes. All the action that we're talking about here really occurs in the two-phase region where you have in thermodynamic equilibrium two phases at the same time. So the net result here is you have to know a great deal about the fluid phase behavior of your system. And that is generally done by equation of state flash programs. But you got to worry about that. So that's quirk number two. There's and sort of quirk number two I'll talk about in a series of about 3 slides. And that some of it is definition. And in fact, I'll give you a hint to the punchline. The thing that makes multi-phase flow so difficult to calculate is that the liquid and the vapor don't necessarily, in fact, generally do not move at the same speed. And this causes all sorts of vexation. But to backtrack, a couple of definitions. One thing that at least in the oil patch, we tend to talk about liquid holdup fraction, which is quite simply the cross-sectional area of the liquid, the cross-sectional area of the liquid in the pipe divided by the cross-sectional area of the total, so that you have liquid holdup fraction, which would be this area of the liquid, and divided by the total pipe area. So you can also talk about gas fraction, which what is the effective density of the fluid in a piece of pipe? Well, it's the holdup weighted average of the liquid densities and the vapor densities. And we'll see in a second, this is profoundly important. There was a slide. I don't care if you, but I'll tell you about it anyway. From that phase behavior, when you know the densities and relative amounts of liquid and vapor, you can determine what are the flowing volume fractions of the vapor and flowing volumes of the fluid. It's a thermodynamic thing. If you know the total volumetric mass flow and you know the relative amounts of vapor and liquid, which you know for a multi-component mixture from a phase envelope, you can tell out what your gas volume, what the gas liquid is. Well, one would say, well, then it's simple. All I had, the holdup fraction that I'm talking about here is simply equal to the flowing mass fraction. I know that from input mass flow and thermodynamics. And the answer to that is no, 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 emphatically no. And that gets back to the point I was just talking about, in that the liquid and the vapor don't go at the same speed. Why should that be? Well, one of them is obviously with inclination. That if you have even a slight uphill, the liquid tends to drain back relative to the gas. So the liquid holdup fraction in uphill flows tends to be higher than the flowing volume fraction. The converse may occur in downward flowing inclined pipes, where the holdup can be less than the flowing mass fraction. So inclination is profoundly important. The other reason, even in that hypothetical case that never occurs in the real world of totally horizontal flow, the liquid tends to be, holdup fraction tends to be higher than the flowing gas fraction, because hydrocarbon liquids tend to be about 3 orders of magnitude less viscous than more viscous than hydrocarbon vapors. Since the pressure drop in each of the two phases is the same, that means and the pressure drop is a function only of axial position. That means that the shear rates have got to be much higher in the gas flow than they are in the liquid flow. I'm waving my hand a little bit, but I'm trying to give you an argument why the holdup has to be higher even in a horizontal pipe because of the differential in viscosity to make the pressure gradient the same in both phases. So almost always, except for some downward pipes, the holdup fraction is higher than you would expect from a no-slip model. And it turns out that this is one of the biggest problems, maybe the biggest single problem in modeling two-phase flow, because a lot of the mumbo-jumbo that I will talk about in multi-phase modeling, the biggest single mumbo-jumbo are the correlations, and I say that it's empirical, between the flowing volume fraction and the holdup fraction. That's one of the things we struggle with. One place where this really comes up, I've already intimated, and that is just pressure drop in a multi-phase line. Now, all of you will remember from your undergraduate fluid mechanics, and remember the sort of extended Bernoulli's equation and a momentum equation. You do a fanning versus Darcy friction factor. But you remember you've got a friction pressure drop, an elevation pressure drop, and the acceleration pressure drop, which everybody ignores. And that really works quite well for single phase flow. But there was a big fly in the ointment in multi-phase flow, and I've already alluded to what it is. What happens if you consider two flow lines? One of them absolutely horizontal, and the other one that starts off at the same and ends at the same elevation. In single-phase flow, it would be clear that they would have the same pressure drop. The elevation head in those two cases would be identical. Every time you went up a hill, you'd lose some head loss, elevation pressure drop, which you would exactly gain back when you went down the same hill. So the only thing that made any difference notice that I just got through saying that the holdup fraction, and hence the effective mixture density, is higher in an uphill pipe than in a downhill pipe. So every time you go over a hump and bump, you have a pressure drop above and beyond the frictional pressure drop due to this holdup effect. So the sorry state of affairs here is that just to calculate the pressure drop in a piece of pipe in multi-phase flow, you need to know something about the holdup relation in the pipe to capture this effect. And this is a new evil that did not appear in single phase flow. It can be a very important evil. And in fact, any of you guys who are interested in a wellbore load-up, this is what you're seeing. You have actually two different regions. If you plot for a constant outlet pressure, you plot inlet pressure versus flow rate. At high rates, you get a friction-dominated region. It's all just the standard 1/2 rho v squared stuff. Exactly what you would think. Exactly the same for multi-phase flow as for single-phase flow. So that's fine, but what's happening is low flow rate. The actual pressure drop actually begins to increase beyond some critical level. What is happening is this hydrostatic effect is beginning to dominate over the normal frictional effects. And in fact, this total curve is simply the sum of a parabolic curve of friction and a sort of asymptotic curve for the holdup. Well, this can occur even in pipelines over hilly terrain. That it turns out that there is a flow rate for which you have the minimum pressure drop. But what really comes into account is in wellbores, where at some point generally right around here, the hydrostatic part becomes dominant.
Hi, excuse me, what's the net pressure here, sir?
Pardon me?
What's the net pressure here? What's no pressure?
Well, and this is sort of a generalized here. The inlet pressure would be the bottom hole pressure, and the outlet pressure would be the wellhead pressure. So what happens is when you get a gas well loading up, is that you get to the part where this gravity-dominated becomes dominant. You can no longer sweep all the liquids out. They begin to collect, have more hydrostatic pressure drop until the entire well will load up until it dies. Again, it's effect of the total pressure drop being a function of both the frictional and the elevation. Again, something you don't see in single phase flow. Another thing that I need to say is another quirk, although it's not necessarily unique to two-phase flow, it's certainly present, is that you really need to consider as much of the system as possible in your simulation, because the different parts of your company who worry about these different parts may not talk to each other, but the fluids certainly do. For an example, this would be a case of this is a hypothetical example of a well, a subsea well that flows along the bottom and comes up in a riser and goes into a separator. And if we actually track the pressure drop throughout the whole system, we start off at reservoir pressure. We get a pressure drop in the near wellbore until we get to the sand phase pressure. That is tracked right here. Then coming up the wellhead, we get a big hydrostatic pressure drop in the flow going vertically. Then when we go across the seafloor, we get a few humps and bumps, but we get some more gradual pressure drop, almost exclusively frictional. Then we come up a riser and get a bigger pressure drop, more hydrostatic, and then we finally come into a separator. And all this stuff counts. You really need to consider as much of this in your simulation as possible. And frequently, due to organizational constraints, the reservoir engineers consider this, and the completion engineers do this, and the pipeline engineers do this, and the facilities people do this. They all want to study the your own system in isolation. Don't do it. It all matters, and you need to talk to the people next door. Okay, enough of quarks. This is sort of another way of saying I'm beating on you guys. Consider as much of the system as possible. The previous slide showed the impact on pressure, but it's also true on temperature. Again, same example: reservoir, bottom hole, wellbore, flow line, top size. And if you track this in PT space, then you're coming down in pressure. You're also coming down in temperature. So the actual PT trace of this flow path can do some strange things. One of them being obviously that you could have gone across phase boundary. You could have gone from a single phase flow to a multi-phase flow, intermediate in the line. Got to study the whole thing to see that it happened. Another flow assurance attribute of this is that while we're cooling out, you may or may not have come down below the hydrate point, to where at some point in the line you may have entered a region in which hydrates are thermodynamically possible, and you can get in trouble from that point of view. Again, from both pressure and from thermal considerations, you need to consider as much of the system as you can. Now, the case that many of you, I've heard you talk about, use nodal analysis. Nodal analysis is a steady state technique to examine a lot of this stuff. You make an arbitrary break somewhere in the system, you plot everything against upstream of that on one flow rate versus pressure curve, and everything down on another one. At some point they intersect, and you can tell a lot from that because it makes it very easy to do parametrics studies on changes in your system. That's great. It's good. I have nothing bad to say about that. The only problem with that, steady state simulation has some limitations in that nothing can change with time. And that's where I would like to depart and talk to you about something that maybe you haven't seen. And really kind of giving a justification. Why is there OLGA? Why do we do transient multi-phase simulation? I'd like to show you some cases that pretty much only transient simulation can do easily. Some examples of them: blowout slugging, rate changes, pinging, blowdown, a whole bunch of operations that actually occur are inherently transient and can be modeled only in a transient sense. One example that maybe you've probably heard me prattling about this in some of the discussions before is terrain slugging. It's one of the sort of prototypical new evils that has come into the world as a result of multi-phase flow in real systems. And this one is fairly simple. In essence, under certain conditions, generally low flow, and certain geometries, your pipeline system can actually oscillate spontaneously. What happens is, if you get a slug, if you get the prototypical geometry is a downward sloping pipe terminating in a riser. When that happens, you can get a blockage at the bottom of the riser, which can then fill up the riser with a liquid column, so that you have a big elevation pressure drop balanced by an increased pressure in the gas bubble ahead of it. When that interface noses under the low spot, you get gas beneath liquid in this riser, which then blows out really quite catastrophically, and so that you get these intermittent slugs that can really be quite long. They can be several order 10 riser heights long, and it will occur periodically. And since it's also an malady of low flow rates, it can occur to you late in the production life of a field. So this is an inherently transient multi-phase phenomenon that nodal analysis, any steady state analysis, can tell you nothing about. One of the reasons why you need a transient it turns out that OLGA in general is in addition to being a very good multi-phase simulator, is also a good transient simulator. And one of the questions that you frequently ask is, if I have, in my, particularly offshore, a shut-in in my system and it starts to cool down, how long does it take to reach a hydrate condition? How long before I have to do something? A very standard flow assurance question. Well, OLGA answers that very well. This is a particular example of some project I did, in which in pressure temperature space, I overplotted the hydrate curve. This is the plot at which, in this region right here, hydrates become thermodynamically stable. And if you start out with a system that is initially under steady state conditions well out of the hydrate region, when you shut it down, the pressure profile changes immediately. But as it sits there and cools down, the entire system cools down until, in this particular case, after about 30 hours, this point right here, which physically tends to be located at the base of the riser, enters the hydrate region. So what this type of analysis tells you is you can sit there and do nothing for 30 hours before you get in the hydrate question. So a lot of design of offshore systems tends to be a trade-off between operational inconvenience and the cost of insulation. This is something that only a transient simulator can tell you. You have the same problem when you restart from the same shut-in. Say that you did all this stuff and you got it cleared, and then you want to start up again. So that you started out, let's see, down here it is. In all your pickle conditions, you started out in a pressure temperature case like this. This was a blown down line. Then everything was fine until you tried to restart the line. Well, what happens? You start getting in high pressure but cold fluid into the line. Since it's cold fluid, you haven't heated it yet, but the pressure immediately goes up, and you immediately get into the hydrate region, in which case you expose yourself to the possibility of hydrate floods. And in fact, you stay in that condition for some 6 hours until you finally have enough warm reservoir fluid percolating into the line to heat things up enough that you get out of the hydrate region. This is the sort of thing that I would argue that only a transient simulator such as OLGA can tell you in a quantitative sense. More examples. Pigging. Put a pig in the line and sweep the liquids out, and you get one big honking slug coming out. In fact, the pigging slug is generally the largest slug that your system will ever see, and this can be very disruptive, particularly from a facilities handling point of view. You just overwhelm your separation capacity. How big is the pigging slug? Well, in one sense, you would say, well, that's kind of trivial, because it's just the entire liquid inventory of the line, which you know from steady state solution. Well, it's not true, because when you're running a pig, all the time that the pigging slug was going down the line, there was liquid coming up out the other end, because the other end never knew there was a pig in the line until the pigging slug arrives. So in general, the pigging slug can be somewhat, sometimes substantially smaller than the liquid inventory. And in fact, you need a transient simulation to determine how long that is. But maybe more important than that, and I don't have a picture on that, is what happens if you just pigged? How long does it take to come back to the steady state condition? Because all the time when you have an empty line and you're putting more liquid into it, the line is just acting like a long separator and collecting liquid inside, and you get no liquid out. How long does this happen? That can be important. In fact, if you talk to gas transmission people, they'll say, oh, we don't have two-phase flow in our line. We just get single-phase flow out. Says, well, do you ever pig in? Says, yeah, every 6 months or so, and get this great big water slug out. Well, they didn't. They always had a two-phase line. They just didn't know it. What was happening is they were operating in the transient condition, which might take 6 months before the line filled up to its equilibrium condition with generally water or hydrocarbon liquids. Again, it's a transient two-phase phenomenon. Let's see, how are we doing for time here? I don't want to bore you guys. I've already talked a little bit about this. Pigging. This is an interesting plot from OLGA right here. This is a function of time starting at pig launch versus a whole bunch of things. The black one is the liquid inventory. I think you can see it comes along here when the pig is coming down the line. And liquid inventory goes down almost nothing. At the same time, you get the big pigging slug out. Well, this is indicative of just how abrupt pigging slugs are. In general, you get a pigging slug, you need the full volume of that pigging slug to be able to be held in your separator because, I mean, you just got to do something with it. But the more interesting part of it is, you see this long rebuild. This is what's happening. The pigging slug is just exited, and liquid continues to come in the line, so the liquid inventory is building up, and it's not for, in this particular kind of trivial answer, it's not till about another hour until you get back to more or less equilibrium conditions, and liquid starts coming out the other end. You need a transient simulator to quantify this stuff, and OLGA does it very well. I guess the final example of neat things that OLGA will do, or any transient simulator, is rate change simulations. And really, you can kind of figure this one out from what we've talked about so far. At high flow rates, a line has low liquid inventory. The gas is really whizzing over the liquid. The interfacial shear stress keeps the liquid swept out, so the liquid inventory is low. By contrast, at low flow rates, you've got high liquid inventory. Less interfacial shear stress, you've got more liquid inventory. Cool. What happens if you're going along at a low flow rate and you increase the gas rate? Well, clearly it has to readjust from high liquid inventory to low liquid inventory, and the only place the liquid has to go is out the downstream end of the pipe. So you can expect that if you increase the rate in your pipeline, you're going to get more liquid than you thought you would have. The quick rule of thumb on that is, well, you can tell how much the liquid was. It's the difference between the two liquid inventories. That's not too hard. How long does it take to come out? In a flat line, it is approximately the time that it takes a chunk of fluid to go from one end to the other. But what happens if you have undulations in the line? You may not get a single slug, you may get a number of them. And again, this is the sort of thing that you can calculate well with a transient program. And you can also quantify this, and you can run a bunch of cases. This is an example of trying to quantify the fact that separated surge volume for whatever of these transient disasters I was talking about as a function of the drain rate. And that's a good design tool for the facilities designers so they can do explicitly the trade-off between slug catcher size and operational inconvenience. Well, I think I've just about beaten that horse to death. By now you should all be fervent OLGA fans. So I'd like to tell you a little bit about the structure of the model. And a lot of you are more into computation, and particularly into Fluent and CFD, will find that this is actually a fairly degenerate model in the sense that it's a one-dimensional model. This is a one-dimensional fluent. How hard can that be? But just to belabor that some, it's sort of a standard oil layer in initial value problem. No real rabbits out here. You can see that in OLGA, it has the mass conservation equation. It has a gas mass equation, liquid hydrocarbon bulk, hydrocarbon droplets, water bulk, and water droplets. Again, this is the three-phase model where we consider both water, and the water can be partitioned and carried either as a bulk phase or in droplets. And the difference between the droplets is that they move at the speed of the gas, so you have to treat them differently. So we've got how it's 1, 2, 3, 4, 5 conservation equations. It's pretty simple. It's all the rate of change of the stuff inside is equal to the outflows minus the inflows. That's all that's here. In an Euler model, you can also play the same game with both momentum and energy. And OLGA has momentum conservation through gas and the droplets. Remember, the droplets move at the same speed as the gas. Liquid hydrocarbon bulk and water bulk. And the momentum equations have a structure that looks something like this. And you can sit here and you can all go to sleep trying to read this. But the thing I want to say is the standard sort of Eulerian formulation. The rate of change of whatever you're considering inside the control volume is equal to the outs minus the ins plus all the source terms. And that's exactly what OLGA does. Now, the thing about here, though, is there's some things, let's look at a couple of these, because everything couples to everything else. Like, in particular, if we went back into here, the mass bulk, there's also mass interchange and there's a momentum interchange between the vapor and the liquid. Well, the momentum interchange between the vapor and the liquid is simply the interfacial shear stress, which gets back to that old bugaboo that I was talking about before, that the vapor and the liquid don't go at the same speed. Well, how much of the same speed don't they go? Well, it depends on the interfacial shear stress. So right here is identified one of the biggest sources of black magic and mumbo jumbo in OLGA or any other multi-phase thing is the correlations. And I say that correlations. They're empirical. They're tuned up from data. They're not basic principles. That gets the correlation between the interfacial shear stress and the velocities. So there is the weak, and other ones, the shear stress with the wall and the 4 or 5 others. And the exact form of them is where multi-phase models succeed or fail. It's empirical. And of course, the same thing with energy flow. This is a bit more honest. Greater change of the energy terms inside enthalpy flow, or the outflow minus the inflow plus the inputs. Energy conservation is pretty honest. We're not fudging too much there. But it allows us to do things like those cool down curves. I'm jumping ahead here. And in addition to that, we have sort of a four boys transient fluid model that we do. The world's simplest finite element thermal model. We consider only a radial world with as many insulation layers as we want, and consider the transient fluid, the transient heat transfer, including the storage, the thermal storage in any of these intermediate level layers. Pretty simple, but very powerful. Now, after getting ahead of myself, let me back up a couple. I'm going the wrong way. So you can sort of see it's standard Eulerian model, 9 conservation equations that feed into a big honking. It's an old line, Fortran calculation engine. In addition, you have to give it some stuff. You have to, on the input side, you have to give it fluid properties. You have to tell it the system you're doing, pipe and process data. You have to do boundary and initial conditions. And in addition, here's all that mumbo jumbo stuff that I was talking about. That's where all the skeletons are hidden. The interactions between these different conservation equations. So OLGA clumps all that together and generates outputs, which the most useful for it is in the form of plots. And that's basically the structure of OLGA. A little bit of thing right here. I'm going one way. Here we have, again, there's that same OLGA simulator. We have that calculates with an ASCII2 input file or a GUI, gets fluid properties via tab through an equation of state model, and spits out a bunch of different types of plots. Pretty standard stuff. Now, since all this stuff is mumbo jumbo, it has to be tuned up by experimental data as facility, and it's in Trondheim in Norway, and it's the system from which most of the data that's used to tune up OLGA comes from. Now, before I run out of time, and before we get run out of here and you guys have, I'd like to talk about something that's near and dear to my heart these days because I think it's a big portion of the future of at least the domestic oil industry, and that's horizontal shale wells, for which OLGA has great application. Let me show you some of this. Let me show you a totally generic but totally typical shale well. This particular well, about 10,000 feet TBD, has a horizontal section of more or less 10,000 feet long. It's got about 20 perforated zones, and it starts off, it's normally pressured, maybe slightly overpressured initially, so it's got about initial pore pressure about 6,000 psi, and it's completed about a 4.5-inch production line with a horizontal section, and this particular one is 2 7/8-inch tubing. And this particular example right now is completely horizontal. I realize completely horizontal wells don't exist; they all wiggle some, but for argument, this one does. So this is a case I simulated and presented in an SPE paper October 4 last in San Antonio. Y'all can get it. It's open literature. Take it, throw stones at it. The interesting feature about this is that this particular case, when the reservoir, well, first of all, when you take this model and it agrees with the observed behavior in the field, newly drilled horizontal shale wells tend to be wonderful. They produce nice and steady. You look like you've died and gone to heaven, and you put your checks in the bank. But the reservoir pressure declines very rapidly because you have a very limited drainage radius. It's limited by the length of your fractures and the thickness of the zone. So the reservoir pressure drops like a rock. This is not good because you get some instabilities. Here's that case with the reservoir, the picture I just showed you. The reservoir pressure dropped to 4,000 psi, and it gets not stable anymore. It's ragged. All the production is coming out in a couple of hour slugs that occur at about 12-hour intervals. A crummy way to run. Even worse than that, if you look in there, you're beating the sand face pressure around by something like 500 to 1,000 pounds every 12 hours. I would argue this is not good for maintenance of your fracture integrity, and you're going to tend to wash the proppant out. So, given their druthers, horizontal shale wells tend to slug, and OLGA does a really pretty good job of simulating it. And the reason is, this is sort of a summary slide on all this, is that the reason that they tend to slug is the horizontal tubing is just too big. The horizontal liner is too big. You never see it. Tend to be 4.5-inch or 5.5-inch, which for the flow rates you find in shale wells, which is in the order of 500 barrels a day less, is just egregiously too large. Why do we do this? Well, the answer is you have to do the fracking operations. You have to have a tubing that big, get all the fracking claptrap down there, and the tube has to be that long enough, that big, to pump the proppant slurry rates at a high enough rate to form the fractures. So you're just stuck with that. Well, so if you go through the fracture horizontal wells are terrible wells by conventional standards. Just god-awful terrible. The PI for 500 section is 0.005 psi, stock tank barrels per psi per day. I mean, that's terrible. You know, in a conventional well, the answer would be 110. This is 0.005. This is why we drilled horizontally for 10,000 feet to expose enough source rock that we could get a formation contact area. And even when we did that, we had to hydraulic fracture it to get more area to expose to more surface to expose the source rock. We're stuck with the liners. We had to do all this stuff. But the hydraulics of this that's important is that for these low flow rates, even for horizontal flow, the flow is in stratified flow in the horizontal section, which means that you have a big gas bubble in the horizontal section. This is guaranteed trouble because gas below liquid. Remember the liquid wellbore, the vertical section, can be filled with liquids. Whenever that gas bubble nose is under, we have exactly the terrain slugging geometry that we saw about 10 slides back, that it blows out uncontrollably. So it's an invitation to wellbore slugging. Another way of putting the same thing is you are routinely taking a kick in your wellbore every 12 hours. This is not a good way to operate, and it is in its native form an unavoidable way to operate because of the very large horizontal section and the resultant stratified flow. I mean, this is a lesson that it's much more apparent when you do a transient simulation. Now, there are a bunch of things that you can do about that, and stay around and we can talk about it. We can talk about this until the sleet stops and it clears off and everybody wants to go home. So that's another topic. But I would like to talk about one other thing before quit chewing on you guys, about one thing that we're not doing very well. And that is something that a lot of you know a lot more about than I do, and that's the inflow performance. I'll tell you, the way that I'm currently doing these is you have production data, and I'm just tweaking the reservoir pressure and a PI to match the observed production data. And that actually does a pretty good job of matching today's data. But what happens, what you're really interested in 6 months or 12 months or 2 years down the road, some forecasting ability. We currently don't have the ability to do that because OLGA standard just uses the sort of steady state, and that's the key word, PI, Forsheimer, OLGA, all the usual suspects. But these are all steady state characteristics and do not have any transients in them. They do not consider the packing and drafting in the near wellbore region, and which is something that we absolutely need to do. Now, we do have an option in OLGA that called OLGA-ROCX, which is just what you might think it is. It's a little bitty reservoir simulator for the near wellbore region, divided up into grid blocks and do the transients on that. Pretty simple and very compact, because you're really only interested. Well, you're not interested in anything out past the fracture radius. So that kind of works, but the geometry is all wrong, because this assumes a conventional reservoir with more or less cylindrical symmetry around there, and that's not what we have at all in fractured shale wells. What we have in fractured shale wells is something more like this. We have clusters of perforations in one perforation zone, and the fractures come out here. The fractures come out here to the fracture radius, and they're limited in the plane outside outside the picture here to the formation figure. So you got a long, skinny thing right here, and the actual diffusion action. This is where you find how dumb we are. The diffusion is actually axial into the perforations in this region right here. So the actual diffusion distance, if in fact that is the process that is happening, may only be that far, or that far, or that far. It depends on any natural fractures that may be present, but certainly it's very limited, and it's in relationship to the actual fractures. So the next model that we'd like to write, and we've begun doing that, is one that incorporates this geometry, but would still have some sort of transient inflow flow performance curve back into the matrix of the rock. And that would be better than we have. that we absolutely need improvement on. Now, there's the other question too. These are shales at very low permeability, and Darcy flow may not even be the mechanism. Well, at least if you went to geometry that acknowledged that the mass transfer was parallel into the fracture zone, at least you could pick that up. So I throw this out to you guys because you're much more sophisticated than we are. The inflow performance part of it, which is not in the tubing, which is not something that I have great experience in, but many of you do, is an area that needs to be tuned up a whole lot. Well, running out of time, running out of slides, just kind of what I've said here. First, I told you that multiphase flow is a number of quarks. I hope I illustrated some of the main ones. Do a number of useful scenarios, particularly in flow assurance. Transient multiphase flow has become a standard workhorse in what's called flow assurance, particularly offshore, sort of a grab bag of all the things that can go wrong with your well to keep it from flowing. OLGA has become sort of the standard, part of the standard toolkit. The OLGA model is inherently transient as opposed to a steady state simulation. And I went into a little bit more detail for OLGA for use in horizontal shale wells because I think that's an important and up-and-coming field. So that's kind of what I had to say. Went about 10 minutes longer than I probably should have, but we still have some time to talk. Come on. You've been sitting here for like... Ask the questions. Uh-huh.